Alright, welcome back to the Boolean algebra slides. Let's finish them up. Not too much to do. These are some shorter slides, which is nice after a midterm, I'm sure. So let me teach you some new circuits, and that will make some things very cool. I promise that it's fun. So first of all, here's an idea. A set of operations is called, a set of Boolean operations is essentially what we're talking about here. A set of Boolean operations is called functionally complete if any Boolean function under the sun that you would like to write can be expressed in terms of only those operations in that set. And so a cool thing to notice is that addition, multiplication, and complement, that is and, or, and not, those are functionally complete. So anything that you write, any row of a truth table that you would like to express, you can express it with just and, or, and not, with just addition and multiplication and complement. Isn't that cool? Or and not, technically, I guess, if that's the order. And we've kind of talked about that, like any fancy thing that we have, like P implies Q, that's really just something involving nots, ors, and ands. It's just not P or Q. So anything, in fact, anything that you want, and make it like the right side of a truth table, it's going to be expressible in terms of and, or, not, because those three operations taken together are functionally complete, which is really cool. All right, that's pretty nice. We have some extra nice circuits or extra nice operations now called NAND and NOR. Maybe you've heard the word NAND before if you've ever like bought your own CPU or looked into how CPUs work. So circuit designers, they really love the NAND and the NOR gates because by themselves they are functionally complete. So that's pretty cool. Here is the NAND operation. You can write it with a symbol as an up arrow, and what it does is it does the and first and then the not. It ands the two things and then it negates them, and apparently with just those you can compute anything under the sun, because you can kind of see how it makes or if you use the De Morgan's law. So this is its circuit diagram. You do the and first and then the not. Remember that the not happens at the little dot with the inverted with the not gate on the inverter. So that's why I had you memorize it that way. So that's the NAND gate. That's how you'd write it out. And so let's just do the and first and then negate it. So first doing the and would put a 1 here and a bunch of zeros here, and then it's negating that to make 1 1 1 0. Hopefully that makes enough sense. That's NAND. And NOR is the exact same idea, but just do or first and then negate it. So it's like do the or of x and y and then negate that. And so remember that or was 0 1 1 1. Negating that, it becomes 1 0 0 0 for these orders of things. Yeah, so that's NAND and NOR, and they by themselves separately are functionally complete. Like or and not are functionally complete, and then just NAND by itself is functionally complete. Same with NOR, so you can pick whichever one you prefer. Doesn't matter. They will both get you to the same place, which is lovely. Let's see here. And yeah, so you can compute anything with just NAND by itself, with just NOR by itself. Let me again give you an idea, that's kind of how that works. If I just wanted to express the idea that not x is true, how would I express that with a NAND gate? Well, I could do it like this. What is not x but the negation of, I can just write x twice because that goes away by the idempotent law, so that's the same as not x. And then what is the negation of an and but a NAND? This is x NANDed with x gives you not x. So anything you want can really be written in terms of NAND or NOR. And the idea, the reason behind this, why would you want this? It's because, well, it's very cheap to make the same gate a bunch of times and use that to do everything inside of your CPU, inside of whatever logic circuit you're creating. Okay? So that's why this is important, and so a lot of CPUs are made just entirely of NAND gates these days. So that's fun to think about. And so that's functional completeness. It's a cool idea, I think. Let's next talk about satisfiability, which is a very, very important problem, and you've solved it already, right? So a Boolean expression, it's called satisfiable. I don't really need to spend too much time here because you know what I'm talking about, given that you did the lab. So a Boolean expression is satisfiable if there is some way to set those input variables that creates the final expression being 1, being true at the end, all right? So figure out if this expression, this fancy large Boolean expression, f of x, y, and z, define that to be x times y, or with z bar, whatever you want. Like figure out if this, my satisfiability engine, so figure out if that is satisfiable. If there's a way to make, to set values for x, y, and z such that the output is 1. That's the idea. So it just so happens that this is a really hard problem. You had to try a bunch of possibilities. Remember, you had to try different values, 2 different values for x, 2 different values for y, 2 different values for z, 1 for every variable. Like you had 2 options. You had to branch every time you saw a new variable. And that leads to like a exponential growth. Like there's 2 to the 3 options for x, y, and z. They're combinations. So the algorithm that you came up with, that I forced you to implement in the lab, was an O of 2 to the n algorithm, which is disgustingly large. All right, it got bigger very fast, and n is the number of variables in the expression. So that's disgusting, and that's about as good as you can do, essentially, unless p is equal to np. So maybe you've heard of that before. So let's go there now. So determining the satisfiability of some arbitrary formula, even if it was nice, like even if it was written in CNF, like it is NP complete, we say. It is NP complete to determine that, and that just means like it's similar to some very, very hard problems that we know about that we're not really sure if there's a quick way to answer them. All right, just means it's really, really hard. So let's see here. Let's talk about P versus NP. Maybe you've heard that before, or you've searched for it on the internet. P is just, it's a set. It's a set of problems or programs, essentially algorithms, that you can compute in polynomial time. All right, so like here's P, it's just a cloud. So things that are in P are like algorithms that are linear, algorithms that are quadratic. That is a polynomial over the input space. That's cool. NP is problems that are verifiable in polynomial time, which is weird to think about. And the question is, like this problem, it's verifiable because it's like you give me an answer for x, y, and z, and you claim that it gives me a 1. I could just plug it in. That's a very fast linear time algorithm to figure out if your answer was correct. But that's what NP is. NP means problems that are verifiable in polynomial time. The question, if P is equal to NP, is like, is there any overlap? Is there overlap here? Because we're not sure yet. This is an unsolved problem in computer science. The best algorithms that we know for these NP-complete class problems, like satisfiability, take exponential time. Cannot do better than them. Cannot shrink it down to be some quadratic, some cubic function. Can't do it. All right? And the idea is, until we prove it, we're just not sure, but we kind of think, most people think, that P is not equal to NP. But we can't really do any better unless P is equal to NP. That's the idea. That will allow all of these hard problems to be in here, and suddenly you get very, very fast algorithms to do fancy things like satisfiability, which would kind of make Bitcoin go under, because it's relying on some very, very hard problems right now. Okay, so that's my spiel about this. It's not something you need to memorize. It's just something you'll learn a bit later in like an algorithms class. But this is the idea. You have some P-style programs and some NP-style programs, and satisfiability is an NP-complete program. It is in NP, but we're not sure if we can do it any faster than some very horrible growth rate. That's as good as we think we can do right now, right? So here's a silly example. Let's encode a fun computation in terms of satisfiability. So here is a fun problem. Tic-tac-toe. Let's have a computer solve tic-tac-toe by encoding it as a Boolean formula. And this is going to show you how anything you could ever want to compute can be encoded with ands, ors, and nots and things. Okay? That's the idea. So let's encode this question. We're going to encode a game board as well. But a tic-tac-toe related question, let's encode that as a satisfiability problem. What ways are there for X to win in some game board? Like you give it a game board, and it's like, what ways are there to win tic-tac-toe? And so maybe you give it this game board, and it's like, let's see, something like this. And then let's say that it's X's turn, or I don't know, doesn't really matter. So you can say like, all right, there is one way for X to win, and it's like this. Something like that. You can compute that. Okay? So given a tic-tac-toe board, what ways are there for X to win? That is a satisfiability problem. You can flip it around to do O as well, but that's a good start, I think. All right. So we can turn solving tic-tac-toe and asking for which ways you can finish the game in terms of satisfiability. Here's how you can do it. So you end up with a bunch of Boolean constraints. It's like an if statement that what is true when X wins kind of question. You'd ask that. So we have to have some constraints on our boards. All right. So essentially, we're going to go to the level of Boolean variables, and we're going to have each Boolean variable represent a place in our tic-tac-toe board. Like here is a Boolean variable 1, 1, B1, 1, B row 1, column 2, B1, 3. So we're going to have 9 variables that could be X or O, kind of. 2, 1, B2, 2. So that's the first part of encoding this question. B3, 1, B3, 2, B3, 3. And each of those could hold X or O, and that could be true or false, right? X or O here, that's fine. It's a Boolean variable. And now we also need to ask the question, like, we have to encode the fact that game boards look in a certain way, right? Game boards are filled in, like, can't have XO and, like, put a P over here or something. You have to encode the rules of the game as well in your satisfiability question to make sure that the computer only comes up with the answers that you want. So first you have to add this constraint. You have to say that in tic-tac-toe, every square is filled by X or O. And so you can represent this fact. There's like a for all in there, but you can break it down to each individual variable if you wanted to. It's like for every square, either the square is equal to X or the square is equal to O. That's the idea, all right? So we're just going to make some big long if statement, because what we need to do is we need to represent. Let me spell need properly. Need to represent what the board looks like. Like, what are the values of these variables when X wins? That's the idea. We need to represent what the board... You can give it a starting variable, starting values for some pieces of the board as well, so it can tell you the best next move. What the board looks like when the game is over and X won. That's kind of the question that I'm going to show you how to ask. When the game is over and X won, because that's what we want to try and figure out. That's our question. So first of all, like, the game is over when every square is filled by X or O. So for all squares, square is equal to X or square is equal to O. And you can encode this as like true for X, false for O. Doesn't really matter. And then also, what does it mean to be a tic-tac-toe game? There is, if you do tic-tac-toe according to the definition of the game, X goes first. And so at the end of the game, there is one more X square than O squares. It's 5 versus 4. All right, so you need to encode that, otherwise, like, it might give you back this answer. Just fill in everything with X. And of course, that's not a valid solution. So you need to encode what it means to be a valid way to win the game. So there's one more square filled by X than by O. We'll assume that X always goes first. So we can make like a count X function in terms of Boolean variables and be like, all right, count X over all of these game board pieces that ends up being 5. All right. And then that taken together with the fact that every square is an X or an O, that means the remaining squares. There's 4 O's, okay? There's 4 O's left. This idea, this formula, it is hard to encode in terms of, like, you have to have numbers. But you can encode everything in terms of ands, ors, and nots. It is possible. The computer's going to do it for us. Smart people have done this conversion for us already. We'll just hook into that. And then we also want to represent the fact that X won and O didn't win, because we don't want the solver to spit out a game board that looks like this, where X also won in addition to O, right? That's a bit silly. That is not a valid game state where you have 2 winners. That won't work, so we need to make sure that that also doesn't happen. So here is X won and O didn't. So like either like X won by the first row, or X won by the second row, or like do all the ways that X could win. And then also and that with the fact that O didn't win any of those places. Like, it's not true that all of the first row is set to O. And it's not true that all the second row is set to O. All the ways that anybody could win, don't let O win. All right, so like we and together these 2 ideas. You kind of see how you can make a big long if statement that represents what it means for X to win this tic-tac-toe game. And then you can let the computer, a satisfiability solver, figure out what the board looks like in those cases. That's the idea, all right? So let's feed this to an industrial scale SAT solver, satisfiability solver. The most popular one these days is called Z3. It's made by Microsoft, and there's a fancy website here that lets you try it out. And so here it is. Just a sample one. You can execute it, reset it. But I'm going to replace all this with a program. Looks kind of like Racket. They use the Lispy syntax. With a program that is going to solve for when this game is over and X or O won. So here is the program, and I'll try and explain it as best as I can. It's a SAT solver program, and so it's like the Boolean variables, or they're not Booleans anymore. We're just going to assume that X, we're going to use numbers instead of variables, but you could use Booleans as well. Let's assume that X is 1 and O is defined as 0. So this is Racket style, semicolon, comments. It's like declare a variable that's an int called b11, b12, b13. So make all your variables, tell the solver that they exist, and then here is my count x function. I also make a count o function. It's just like over all your variables, is it true? This stands for if then else. IT stands for if then else. If b11 is equal to 1, that means it was an x. Then count it, make it a 1. Otherwise, say 0. So like it's a 1 everywhere it was an x. So add up all the places that it was an x essentially. So one big plus. So that's counting all the x's. And then the same thing for the o's. It's like put a 1 here if this was equal to an o, which is a 0. We're encoding an o as a 0. So add up all the zeros and make sure that give back that answer. All right. And then the rest are all our constraints. There's also like, did somebody win? Question, like, did somebody win the rows? Like, did this player, it takes 2 variables, did this player win the game? Or I guess it just takes a single variable. Sorry, this is a solver level function essentially. It's like, did somebody win? And here's the person. Like, did X win? Did O win? Because we're encoding the players in terms of integers. Again, I'm not really going to test you on any of this. It's just a fun idea that you understand now because you've implemented it. You know how hard this is. So yeah, here's how all the rows could be won. Like the player, like we're given X or O, like is like all of the first row set to that player's variable? Is all of the second row set to the player's variable? Because one of these ways, if any of these are true, like or them all together, the rows, columns, the diagonals, all the ways for the player to win, if any of those is true, then it's true that particular player won the game. All right. And then finally, with all of those helper functions defined, we can write our constraints that we want the solver to solve. This is going to turn into some big long if then else, or a big long condition for the solver to figure out. And so it's like assert that count x, whatever is true about count x. Call that function essentially. It's by itself. Assert that that's equal to 5, and count o is 4. So every square is filled by x or o. That's asserting that, making sure that's true. And then we want to make sure that also there's one more square filled by x. That's the 5 versus the 4. We also want to make sure that x won. So assert that 1 of 1 is a true statement because 1 is encoding x and 0 is encoding o. All right. And then also we want to encode the fact that o did not also win the game because that is not what we want. We don't want to get to a game state that looks like this. All right. So that's how you use this solver, and it's going to very quickly convert this and figure it out. So it's like assert that o did not win, assert that not 1 of 0 is true. All right. And then these last 2 things say check satisfiability, like figure out if there's any solutions at all, and if there are, give me some solutions. All right. And it'll just give you one. You can ask it for another, and by saying, I don't want this one, I don't want that one. But that's the program. Hopefully it makes at least a little bit of sense. And then if I run it, it's going to give me one way for X to win and O to lose. So here it is. It's like, here are your values. And if you zoom in and squint, like it's got some helper variables that it made for itself, and it's got our original variables that we care about. Like this all works out if B12, for example, is set to 0. That's the idea. All right. So let me draw out this board that it's computing. Set B12 to 0, and so that's row 1, column 2. Set that to O. 0 is O. B13, set that to X. B32, set that to 1, it's telling us. So that's X. 3, 2, X. It's just giving me back one way for X to win. B21, set that to O. let's see here, B33, set that to X. So maybe it's this way, I don't know. We'll find out. B23, set that to O. Okay, so X didn't win that way. Let's see what way it's gonna win. Could be this way or diagonal. B11, set that to X. Ooh, that's promising. Then B31, set that to O. Okay, so this must be the way that it wins, by the diagonal. There's just one way, the fastest way I could find, that satisfies our solution. B22, set that to, of course, an X. And so that is how the solver came up with, here's one way to make X win the game according to all of your constraints about, like, you have to have this many X's and O's, you have to make sure that X won and O did not. That's what you have to think about when you're using a sat solver. And so you know how to solve for satisfiability, and now I've kind of just taught you how to ask a satisfiability solver a useful question. Okay, so that is what I wanted to talk to you about, and hopefully that makes enough sense. So I can help you encode things that you might want to encode in the Z3 syntax. So that's a fun little idea, I hope. And there's not really any way for me to test you on it. It's just a cool thing that I wanted to show you. So that was a very fast exponential time algorithm working for us. It has some secrets to make this program execute faster and find a solution, but that is definitely beyond the scope of this class. So yeah, that is sat solving and one of its uses. All right, let's move on now to simplifying formulas. One way to simplify some very long Boolean formula is by using what's called a Kmap, which is short for somebody's last name. Kmap, Kmap for short. What that is, it's a graphical way of writing a Boolean expression, and that helps you simplify it. So make it shorter. And the reason you would want to make a Boolean expression shorter is because it's easier to type into your program, of course, and then also if you're gonna if this Boolean expression computes something and you're making a circuit to do it, then you're going to use fewer logic gates if it's a simpler formula, and that's going to translate, of course, to less money. And we all like to pay less for the same thing. Okay? So yeah, the idea is instead of taking your formula, like you have a truth table, you kind of read it off and you turn your expression, whatever it is, instead of into a truth table, into this kind of truth rectangle. And it looks different depending on how many variables you have. Here's one for 3 variables. And you try to find patterns in this rectangle, and I'll show you what that means. What you do is you have to have your formula somewhere. You have to figure out what it is, like when x is 0 and y is 0, when x is 0, y is 1. Like try them all out. What does your formula say? And then write those answers in here. That's what you go and do. Okay, so with that in mind, let me teach you how to use this Kmap, this Kmap thing. What you do is you're going to circle groups of 1s, and the groups better be of a power of 2 size. So they better be of size 1, 2, 4, or 8, or 16. I guess you don't have 16 here, but you get the idea. And the groups that you find better be like, here's a group of 1. There better be rectangles or squares, like here's a group of 2. Here's one way to make a group of 4. Here's another way to make a group of 4. You cannot do things like this. You can't be like a Tetris piece, like there's a group of 4. No, it's got to be rectangles and squares only. But when you find them, they will give you your answer very quickly. All right. Also, the square doesn't use the normal kind of order. It's like it uses like A is false, B is true. A is false. A is false, B is false. A is false, B is true. And then it goes and jumps straight to A is true, B is true, and then it goes A is true, B is false. So A is 1, B is a 0 there. So it's it's a kind of a weird order. And then also this is saying that C is false for all of these, and C is true for all of these. So like this particular row right here, put a 1 if it's true when A is false, B is true, and C is true, right? An example will help this make sense. But the idea is you filled this all out. Like there's a 1 here, a 0 here, some 1s, and then like some 1s here. And you're going to circle every group of 1s that you see. And the groups better be of size that is a power of 2. So like here's a group of 4. But I can actually do better. I guess it's about the same. Here's a group of 2 and here's a group of 1. I could also do that in a different way. Like here's a different group of 4. Makes no real difference. But that's a nice group of 4. Here's a nice group of 2. You just search for these patterns. And then here's a group of 1. This one's kind of left out because of that 0 next to it. Can't really do any better than that. So that is one way to make a Kmap and to solve for its answer. And these ones that we circled are going to give us a way to simplify our formulas. It's going to be great. All right, so let me walk you through how you do that. Here is an example of Kmaps. So let's use this Carnot map, this Kmap idea, to fill in the truth values for this expression. Not A, ANDed with B, ANDed with not C, ORed with A, B bar, C bar, plus A, B bar, C, plus A, B, C bar. So that's multiplication, which means ands. So this is essentially a disjunctive normal form, right? And so we can draw a 1. Like this is telling me when a single 1 is true. So when A is false, B is true, and C is false. A is false, B is true, and C is false. So this one, that is a 1. That's what that's saying. Okay, if that makes sense. And then I do the rest. So when A is true, B is false, and C is false. So C is false, A is true, B is false. So this one, that's a 1. That's a 1. And then this one, what's it saying? It's true when A is true, B is false, and C is true. So they're here. And then A is true, B is false. So, oh, sorry, not that one, but this one. So there's a 1 there. And then finally, we have a 1 when A is true, B is true. So that's this one. And then C is false. So this one. So that's where I put a 1. So I'm just reading off, like you can convert this to a truth table if you wanted to and figure out what the right answer is, but that's where my 1s are going to be, and there's going to be a 0 everywhere else. All right, and now the game is circle groups of as few groups as you can find. That's the game. Circle find as few groups as you can find, because technically I could have like circled a bunch of 1s. No, you want as few groups as possible, as big as possible. Groups that are powers of 2 in size. So I guess there's only one way to do it in the fewest number of groups. It's like here's a group of 2, and here's a group of 2. Yeah? That's the idea. So that is a simplified statement there. And let's use a Kmap. Let me show you how to use a Kmap now to find a simplified version of the expression. And I cannot really write down what the right way to do it is. I just have to show it to you. All right? What you do is you look for what is the same. You look for what is the same in the groups that you circled. And, of course, words make no sense. I have to show it to you for this to make any sense at all. So, like, we noticed that we circled this group. It's got 2 1s here. What is true about these particular 2 variables? What in the world is true? Because sometimes, like, right, when we're here, like A is true and A is false and B is true. When we're here, A is true and B is false. Or, sorry, I can't do it today. When we're here, A is false and B is true. When we're here, A is true and B is true. Okay? Notice that, like, that means it doesn't depend on the value of A, because, like, it's a 1 even when A is false, or it's true. Like, A means nothing here. All right? But what is true about this, B is always true. You see, when we're here, when we're in this particular group, B is always true. And also, C is always false. You see what's going on there? So the A doesn't matter. The A is not helping us. The A didn't contribute to this group, but the B did and the C bar did. So that is what you extract from that. You say, B is true. That's the commonality. Like, B is true here, and C bar is true. So B and C bar. That's part of the way. That's going to put the 1s here if you write that out. Okay? I hope that makes at least a little bit of sense. And then this one, what is true about this one? Well, doesn't matter about C, because C could be either true or false. So I can't say anything about C. That's not holding steady across this group. What is true about this at the same time in terms of the variables is that A is always true and B is always false. C oscillates, so C is not helpful. But these, we're always in this column, so it's always true that A is true and B is false. So we'll write that out. A is true and B is false. All right, and that's going to give us the 1s here. And we want 1s here or here in both places, so we're going to OR together those answers. And so this is now a simplified version. It's much smaller, right, than this one. And I hope you see how useful it is. It's going to take some practice to understand why it's working, but hopefully at least you can see how useful it is, right? So with that in mind, let me give you this example. So use a Kmap to fill in the truth values for this expression, this fancy one, and then also use that to write a simplified version of that expression. So let me go and write it out for you. So let's take this, copy and paste it kind of. So you got your A bar, B bar. The reason it's written in this order is because there's one difference as you get to the next column. It's like, what changed? There's one thing that changed. It was the B. The B got negated to be positive B. All right? And then to get here, the A got negated. Now we have positive A. There's only one thing that's allowed to change among these, and that allows you to write this out and simplify it. And then we'll negate the B. That's our one change. And then we have not C and yes C. So there is my table. You're welcome. Please fill it in, and then please try and simplify your expression, right? So that is the idea. Okay, so, all right, when A is true and A is false, is that ever possible? I don't think I can have A true and A false at the same time, so this is not helping at all. That was a useless thing to write. Same with C true and C false, I believe. You can't, like, there's no column in which those are both true. So it looks like these ones are the helpful ones, BA and then B not A. So BA is true when AB, like this. So there's a 1 here and a 1 here. Doesn't matter about C, right? And then BA bar, which is same as this one, A, B bar, right? So there's a 1, let's see. It looks like, oh, sorry. No, it's A bar. A bar B, sorry. That is this one, and that is a 1. In either of these cases, it doesn't matter about C. It's like if it's true if A is false and B is true. Those are our ones. And then, again, you can't find a column where C is true and false at the same time, so that's unhelpful. So you'll write a bunch of zeros here, and you might think, if you just look at this without doing a Kmap, it's like, all right, this one's useless, this one's useless, these have the meat. You might think that that's as good as you can do. You might think that the best answer is BA ORed with BA bar. So those are the two useful things. And, well, before you learn Kmaps, that might be true, but now we have Kmaps. Do you see one big group of a power of 2 in size that is a rectangle or a square? There it is. Oh, man. Let's use that idea. Here's my one group to write a simplified version of the expression. And so the idea is, among all these ones, among all these rows, what is the same? What is not oscillating? Like C is unhelpful, right? Because C could be 0 or 1 here. That's not contributing to this. All right, what about these? Well, we have A is true and false. Like A is flipping between these. A is not helpful. You see that? The only thing that is the same across all of these ones is that B is true. Do you see that? B is true in all of these cases, and that's the only thing that's the same. And that's how we solve the Kmap. The answer is B. That is the simplified expression. Just say B. Do you see that? And I encourage you to write this out. Like all of these other cases, like B is false. You see that? That's the 0. B is a 1. When B is true, the whole thing's true. See how that's the simplified version of the expression? That's even better than this thing. Isn't that lovely? So that's the power of Kmaps, and hopefully this writing makes at least a little bit of sense now. Like you look for what's the same, what's not oscillating, what is not changing values among all the ones in your group. Like that's just B. B is the one thing that is staying the same, and so that's the only thing that contributes to this group. That's the idea. All right. So that's Kmaps in a nutshell. Karnaugh maps, very helpful, and I sure would rather pay for a single logic gate, just run the wire from B to the output rather than paying for a bunch of ands, ors, and nots. Yeah. Okay. With that, I just want to give you a quick little sneak peek of, I won't test you on this, of CSCI 45. Because if you're taking all these classes in order, like this is your second to last one, this is the one you take before CSCI 45, even though it doesn't really require this class. That's just the order that we encourage people to take these classes in. But let me prove to you why this is all useful. All right. So circuits are cool maybe, but like what's the point of learning how to draw these fancy things and like computing these things and simplifying these things? Well, I guess the first answer is, of course, our computers, they're thinking in terms of logic gates. Our computers are nothing but big circuits of ands, ors, and nots. Really, they're just a bunch of nands together, but you get the idea. Well, how do you make a computer do cool things? How do you make a computer do fun stuff out of just a bunch of gates? And I can't tell you every reason. Like, I can't solve computation for you. That'll be the topic of CSCI 45. But I can show you now how computers add. Let me show you that. So here is a gate that helps us add together numbers. So let's pretend you have a bunch of Boolean variables, which are digits, binary digits, bits of a number that you want to add. Remember how to add binary numbers, first of all. 0, 1, 0, 1, 1. So like if I'm adding these two binary numbers, what happens? We have 0 plus 1, that's a 1. 1 plus 1 is 3, and 3 in binary is 1, 1, so we have to carry that 1, 1, 1. And then, again, we have 1 plus 1, that's 1, 0, because that's 2 in binary, so we have to carry, put a 0 here. Again, carry, put a 0 here. And then this is 1 plus 1 plus 0, so again, we carry, put a 0, but there's nowhere else to carry, so it's just 1, 0. And so that's the sum. And so, if you think about this, you can translate this into logic. Like each digit, each bit is just a single Boolean variable, and then their sum is some output variable. You got some wires in and some wires out. So here is how you can use circuits to add numbers. It just so happens that the XOR gate, if you think about it, the XOR gate is doing 1-bit addition. This is a single bit. So take a bit A, bit B, and the XOR, if you do XOR of those two things, those two bits, you get the solution, you get the sum. Like if A is 1 and B is 1, if you exclusive OR those together, you get 0, because that's the answer you have to carry still, right? The sum will be 0. So exclusive OR is doing 1-bit addition, which is really cool. Let me prove that to you. A, B, and then like A XOR B. So you got your true, 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 false, false, true, false, false. And then exclusive OR is like it's true when they're both true, false otherwise. Or sorry, it's true when they differ. True when they differ and false otherwise. And that, if you think about it, it's addition, right? Because 1 plus 1 is 1, 0. The digit for that, the sum for that digit is a 0. 0 plus 0 is still 0. And then here is a bunch of 1s, like 1 plus 0 and 0 plus 1. The sum is 1. So it really is, it matches, true and false. Isn't that cool? So exclusive OR is doing addition. And if we chain a bunch of those, like we have to have like, you put your 1s in, then you have to have the sum, like the output there. Oh, sorry, I don't know how to add. I think I saw 3 numbers somehow. Excuse me. It was just 1 plus 1, so it was 1, 0. Sorry. Carry the 1, put a 0. It was the 1 and then the 0. Excuse me for doing binary addition wrong. So yeah, if you add 1 and 1, the sum for that bit is 0. That's what exclusive OR gives you. And then you also need to carry to the next sum. So there'll be another exclusive OR working on 3 numbers at once. And so how do you know if you need to carry? It's when your 2 inputs were both 1. And how do you know when 2 inputs were both 1? You AND them together. And so my carry is 1. You see that? And we're just going to feed that to the next guy. Isn't that beautiful? So this is 1-bit addition of 1-bit addition of A and B, and this is 1 if we need to carry. All right, so I guess I can draw that over here. So yeah, this is 1-bit addition of A and B. That's why we do that one. And then this is the carry. This is 1 if we need to carry, 0 otherwise. 1 if need to carry, 0 otherwise. And I think I drew this on the wrong slide, so sorry about that. Let me take what I drew here. This is going to be weird, but let me do some surgery here. I'd like to show you this on this slide. because I want to show you how it like feeds into everything. So let's put that over here for a second. And then I'm going to copy and paste this here. There. That's what I wanted to say, and this is where I wanted to say it. So let's move that to somewhere useful. Didn't really write it very well, but I think you get the idea. What if we need to carry 0 otherwise? I'll rewrite otherwise so that you can still see it. So that's the goal there, 0 otherwise. And then here's what happens. Like if we're at this bit, like we're adding the 1 and the 1, that creates, oops. Oh no, did it not copy properly? Oh gosh. All right, let me just rewrite it. 1-bit addition of A and B, and 1 if we need to carry 0 otherwise. Okay, so that's what I wanted to write on this slide. And then this one is where I wanted to show you my example. So, for example, if we have A and B being 1 and 1, then what we need to do, like that was this bit, the answer for that bit is 0, and then we have to carry a 1. So, here we go. The answer for that bit was 0, and we carry a 1. And the idea is we're going to chain a bunch of these together. Like here's the next 2 bits. The next 2 bits in this equation are, we got a 1 and a 0, for example. Got a 1 and a 0 going on. And the idea is this carry is part of the it's part of the addition. Like this is coming out and feeding into this exclusive OR. You can do an exclusive OR on 3 things. That works out just fine. So take this and like put it in here as well, exclusive OR all 3 of these things, and then that's going to be the sum, the 1-bit sum of this answer. So it's 1 plus 1 plus 0. If you exclusive OR all those together, you get 1. So there's a sum there. And again, the carry is were any of these like a 1. Okay, that's the idea. The carry for this one is going to be like, are any of these a 1? Because we're going to bring this in as well. So you need a different, like, one that works with 3 instead of just 2, because this is going to also want to carry, right? Because we have a 1 plus a 1 plus a 0. Like, are any of those a 1? It doesn't really look like that, but you kind of get the idea. Okay, so yeah, that's how computers add numbers. If you just chain a bunch of these things, they're called half-adders. You can chain them together, and it all works out. Really what you want is a full adder that has a carry in and a carry out. Like this is not quite correct, like that's not what you want to do. It's essentially like, is there an and here, and 2 of these together, 2 of these, like or, and see if any 2 were true, something like that. That's what's really going on, but that's beyond the point. That's a topic for CSCI 45. Okay, so this is how computers add numbers. I think hopefully with this example you get a feel for how computers could do anything. If all I need is exclusive OR to add numbers, well, it's not too hard to make the jump from, okay, I can probably do arbitrary arithmetic, arbitrary computation with just a bunch of ands, ors, and nots. Maybe some exclusive ORs. But it's all functionally complete. Ands, ors, and nots do it for you. Okay, so that's a taste of CSCI 45. Look forward to that and this kind of low-level stuff if you're interested. That is the class for it. So yeah, that is Boolean expressions and Boolean algebra in a nutshell. It's just logic all over again, isn't it? Okay? So with that in mind, I think we have a lab that I need to release this week. So that is the next video I will record, and I will see you in the lab introduction video.